Hello students, we will know about geometric distribution and binomial distribution formula in this segment. Okay, so to start with geometric distribution, we're going to discuss a problem. The problem states that suppose you are rolling a die repetitively. Let's say rolling a 6 is called success and you stop rolling the die right after the first success. Okay, so you keep rolling the die until you get a 6, and whenever you get a 6, you stop. Find the probability that it will take you exactly 7 turns to be successful. So here in this figure you can see that it's one of the configurations that the first die doesn't show a 6, nor the second, third, fourth, fifth, and sixth, but at the 7th turn we get a 6. What we are looking for is to be unsuccessful for the first 6 rolls and then be successful at the 7th roll. Let's get back to this figure. Okay, so we want either a 1 or a 2 or 3 or 4 or 5, but 6 in this first turn. Okay, so what is the probability of rolling a 6 in the first turn? We know that that is 1 by 6. So the probability of not showing a 6 up is 1 minus 1 by 6. So it will be same for the second roll and the third, and so on until the 7th turn. So in the 7th turn we want a 6 to show up, therefore the probability will be 1 by 6. Now all of these events have to happen together to get our expected event done. Therefore the probability would be the product of these fractions, right? So 1 minus 1 by 6 to the power 6 times 1 by 6. Now if we say that the probability of getting a 6 is p, which is 1 by 6 in the case of this problem, then the probability of not rolling a 6 would be 1 minus p. So if the number 7 is denoted by n, the number of trials is 7, we want to be unsuccessful for n minus 1 turn, right? For all the turns except the last one. Therefore 1 minus p should be raised to an exponent of n minus 1 for n minus 1 consecutive experiments, and then the final experiment needs to be successful. So therefore the probability is like 1 minus p to the power n minus 1 times p. Okay, so we are not going to simplify our result right at this moment because we are going to derive the formula from these examples. So this is the final result. This is answer for our question 1. Let's see another example. In the example 2, you are appearing at 6 consecutive exams. Probability for you to pass each of the exam, which is denoted by small p, is 4 by 5. Once you pass an exam, there's no need to sit for the rest. Alright, so if you pass any of the exams, you are not required to sit for the remaining exams. So what is the probability that you pass having sat for all 6 exams? So you have to pass, but you have to sit for all 6 exams. Therefore, the scenario means that you have to pass at the very last exam. All right. So what is the probability of that? So you want 5 failures from the first to 5th exam, and then you want to be passed in the 6th exam. Now these doors represent the results of the exams. So you fail in 1. What is the probability of failing in the exam 1? You know that the probability of passing the first exam would be 4 by 5. Therefore, the probability of failing would be 1 minus 4 by 5. So, similarly, the probability to fail in the second exam would be 1 minus 4 by 5. And so on for the next 3 exams, except the last one, right? You want to be passed in the last exam. Therefore, the probability of passing would be 4 by 5. Now, all these events have to happen together again. So, the probability would be 1 minus 4 by 5 to the power 1, 2, 3, 4, 5, so which is 5 times 4 by 5. Let's see the analogy. Say it's the probability of P, which is the probability to pass in each exam. Now the probability of failing would be 1 minus p. So you want to be failed in the first n minus 1 exams, right? If there are n exams you are taking part in, then you want first n minus 1 to be unsuccessful. So therefore the probability would be 1 minus p to the power n minus 1 again. And then at the last exam you want passing, therefore times p. So yeah, 1 minus 4 by 5 to the power 6 minus 1, right? Times 4 by 5 is the result for the second question. So we can sense some similarities in these scenarios, right? Now let's go to our formula, geometric distribution, and let's try to see what it's explaining here. Geometric distribution. If we repeat an experiment until success occurs, where probability to succeed in a single experiment is p, then the required number of trial to be n has a probability 1 minus p to the power n minus 1 times p. So this is a pretty long line and it doesn't make that much of a sense. So let's see what we are trying to say here. The number of trials of the experiment you are conducting is suppose n. Okay, the total number of experiments is n. Now you want to be unsuccessful for the first n minus 1 times. So number of unsuccessful trials equals to n minus 1, right? Now each of the experiment has a probability of success equals to, say, it's small p. So the probability to fail in an experiment would be 1 minus p, right? So you want to fail for first n minus 1 times, therefore see, failure, 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 failure. So 1 minus p should be multiplied for n minus 1 times, and for the last turn you want to be successful, therefore the probability would be p. Therefore the final result would be 1 minus p to the power n minus 1 times p. I hope you understood it right now. Here's an exercise for you to solve, and the question asks that if a coin is flipped until a head shows up, so what is the probability that you need to flip the coin 101 times to get the first head? So here's a figure for you. Suppose all of these are tails and the last one is a head. So first you have to determine the probability of getting a head, which can be referred to as success. So P of H equals to what? And then you have to determine the probability of failure in a single experiment equals to what? And finally use the formula. Now for binomial distribution, we're going to see a few more examples, and we will have similar scenarios of the examples from the geometric distribution part. Now the question is, suppose you are rolling a die repetitively, and let's say rolling a 6 is called success, right? Find the probability that you would be successful exactly twice after rolling the die 7 times. This is the question. So you're rolling the die exactly 7 times, and what is the probability that you'd get exactly 2 successes? Which means you'd get exactly 2 sixes out of 7 times. So now to solve this problem, there would be some steps. Step 1 is find the probability of a particular configuration that satisfies the condition described. Because you know that if you roll the die 7 times, then the first 2 results can be 6 or the last 2 results can be 6 in many different ways. 2 of the results from the 7 turns can be 6. Okay, so you are going to consider a particular configuration from all of them and then find the probability for it. Okay, so look at figure 1. In figure 1 we see that the third and the 7th roll showed success. Okay, therefore in the 7 turns there are 2 successes, so it satisfies the condition. So what is the probability that if the die is rolled for 7 times, the third and the 7th turn shows 6? Okay, so you know that the probability to be unsuccessful in the first turn would be 1 minus 1 by 6 again. For the second turn, it's also 1 minus 1 by 6. For the third turn, it would be 1 by 6 to be successful. Fourth turn, unsuccessful. Fifth, unsuccessful. So for sixth and success in the 7th turn. So for all these events to happen together, the probability would be the product of these fractions. Now there are 1, 2, 3, 4, 5. 5 unsuccessful experiments will raise the probability of 1 minus 1 by 6 to 5. And then there are 2 successful experiments which will leave us with 1 by 6 squared. So this is the probability of rolling 2 sixes in the third and 7th turn. Now step 2. Step 2 asks you find how many satisfying configurations are possible. So you know that if the successes showed up in the second and the fourth turn instead of the third and seventh turn, it would also satisfy our condition of the question. Okay, so we have to find out in how many different ways two of the results from the seven can be picked where we want success. Okay, that's pretty simple. There are seven results and you want to pick any two where you want successes. So 7C2 is the number of cases or the configurations that satisfy the question. Okay, so it could be explained in a slightly different fashion, which is, say, for the seven rows, you have seven different boxes, and you want to put 2S and 5F in all these seven boxes. 2S for two successes and F for failure. Therefore, you're actually counting the number of ways you can make a 7-letter word where there are 2S and 5F. Okay, so if all of the letters were different in the word, the result would be 7 factorial. But since there are two repeating S, so 2 factorial should be in the denominator, and it has to be multiplied by 5 factorial for 5 repeating F. Okay, so you see that 7C2 is equal to 7 factorial by 2 factorial into 5 factorial. Any of these methods were good. Now, if we calculate the value, it would be 21. So there are 21 different configurations that satisfy the condition in the question. Now, the part that I want you to note very carefully, okay? And that is, all of these cases, all of these 21 cases have the same probability to occur, right? Because you know that 2 success will contribute 1 by 6 square in the probability, and the number of failure is 5, so 1 minus 1 by 6 to the power 5 will be coming from failed turns. Okay, so 1 by 6 squared times 1 minus 1 by 6 to the power 5 is the probability for each of these 21 cases. Okay, therefore we can say that if the probability of the first case, say this was the first case or the first event, we call it C1, and the probability where P of C1, then P of C1 will be equals to P of C2 would be equals to P of C3, P of C21. All of these cases will have exactly same probability, which is equals to 1 by 6 to the power 2 times 1 minus 1 by 6 to the power 5. Now for step 3, the final result is the union of all these cases, because you know that either C1 or C2 or C3 or C21, if any of these cases happen, we are cool with it. Therefore, P of C1 union C2 union C3 up to C21 would be my final result. Now you know that these events are disjoint, therefore the probability would be simply the sum of all these results. Now you know that each of these values are equal. Therefore, we are going to replace them by, say, P of C1. Okay, so how many P of C1 are here? You know that there are 7C2 number of P of C1 here, right? So P of 7C2 times P of C1, which is our final result. Yeah, this is the final result, right? Now, I want to set an analogy here, which is, if you are doing an experiment for n times where you want exactly r successes, you can choose r successes from n experiments in NCR different ways. Okay, now let the probability of success in a single experiment is p. Then since you want exactly r experiments to be successful, therefore the probability will have p to the power r coming from the r successful experiments, and then the number of unsuccessful experiment would be n minus r, right? Therefore, probability of being unsuccessful in a single experiment is 1 minus p, and it has to happen for n minus r times, so power would be raised to n minus r. So this is actually the formula. We're going to see another example and get a similar result again. Okay, so example 2, like our example 2 of geometric distribution, you are appearing at 6 consecutive exams. Probability for you to pass each of the exam, which is p. What is the probability that you pass exactly 4 of total 6 exams? Now you have to pass 4 of the 6 total exams. Similarly, like the last problem, we're going to calculate the probability for a particular condition. Say this is a configuration where we pass in exam 1, 3, 5, and 6. So we fail at exam 2, 4. Okay, there are 6 exams in total. So the probability of passing exam 1 is 4 by 5, 4 by 5, 4 by 5, 4 by 5. And failing in the second exam would be 1 minus 4 by 5, 1 minus 4 by 5. So again, we are going to multiply them. So the final probability would be 4 by 5 to the power number of successes, which is 4 here, which is 4, times 1 minus 4 by 5, which is the probability of failure, to the power number of failures. What is the number of failure? There were 6 exams, 4 are successful, so the number of unsuccessful exams would be 6 minus 2. So this is the probability of a particular configuration. So how many configurations are there where we pass 4 exams out of 6? So you know that from 6 exams, you can choose any 4, so 64 number of ways to pick any 4 exams to pass. Now the final result would be, say it's A, so it's 64. Probability of a particular configuration that satisfies the condition is M, and the final result would be, sorry, this shouldn't be P, it should be replaced by M, as we've already taken P for something else. So A times M is the final probability, because you know that there are 64 number of cases and all of these cases have the same probability equals to M. So therefore all of the M's added will be equals to A times M. So A equals to 64. Final result is 64 times 4 by 5 to the power 4 times 1 minus 4 by 5 to the power 6 minus 4. Alright. So now we are ready to see the binomial distribution generalization. So it says that if we repeat an experiment with probability of success at a single trial equals to small p, okay, then the probability of exactly r successes out of n trials is NCR p to the power r times 1 minus p to the power n minus r. How did we say that? We know that the probability of success in a single experiment is p, so the probability of failure in a single experiment is 1 minus p, right? Now the number of success required is r, that means the number of successful trials required is r, and the total number of trials is n. So the number of ways we can choose any r trials to succeed from n is NCR, right? Therefore, the final result would be NCR times p to the power r, coming from the r number of successes, and 1 minus p to the power n minus r, which is coming from the n minus r number of failures. So this is simple. This is a part of our chapter 2. So if you want to see examples, you have to go to chapter 2 of rigorous elementary probability for applications. And if you want to solve example problems, there are examples, and for exercises, you can see the exercise of rigorous chapter 2. Only the binomial distribution part. All right. Thank you.